Okay, so today we are going to talk about trigger in nuclear physics experiments. There is another name also for this, which is channel selection. Okay, now the basic idea is, you see, in any physics experiment, what happens is that several type of what is produced, several type of, even if one reaction takes place, as a result of it, say for example, let me talk about right now compound nuclear reaction. So suppose this reaction takes place where B star is your compound nucleus. Okay, now when it decays, there are several possibilities. Say for example, just let me write it down. Say proton plus X1. Okay, this is proton plus this is one nucleus, daughter nucleus being produced. Another possibility is say 2p plus X2. Maybe next is alpha plus X3. Next is your see alpha n plus X4. Next np plus X5. Just right now, for the time being, consider these 5 possibilities. Suppose such a reaction takes place, and the thing is that these nuclei X1, X2, X3, X4, X5, they have already been more or less studied. But this particular nucleus X3, we do not know much about it. Okay. So now, right now, we want to study this nucleus. So what do is that we make this reaction happen such that the population of X3 is comparatively large, so that we are able to see its excited states being decaying to other low-lying excited states. Do you understand? If the reaction cross section is large for this particular channel, then only we will be able to study X3. Okay. So now the thing that I was talking about, so see, this is a typical reaction of a physics experiment, and now we want to particularly study this particular nucleus. So basically we want to study this particular channel. This is one particular channel. So this is what we are going to do. We are going to select this particular channel out of this. Okay, you understand? Now these are all important. It's not that this is not important. These are all important. But right now our primary interest of study is this particular channel and this particular nucleus. So for this, all the others are what? Sort of unwanted or background. So this means in a basic physics experiment, when there are lots of events simultaneously being produced, lots of products being produced, you have to select. This is important. This is the real stuff, selection of a particular reaction. Say for example this case. Okay, you have to select this. Now this selection can be done from background. Suppose none of these reactions take place, only this one takes place. But when you are measuring the product X3, at that same time some cosmic event or other background, room background or earth background or other backgrounds are there, from there some gamma ray interferes with your experiment. Okay, such a thing do happen. So you have to take care to remove the effect of all those backgrounds. Here we have to take care to remove the effect of all of them together, right? So that we can study this particular nucleus. So you see, this we are going to achieve using coincidence between 2 or more detectors. Number 1, and the entire electronic logic required for this selection is known as trigger. We have already talked about this trigger when we have discussed active shielding. Remember, this was last day when I talked about various ways of improving the peak to total ratio. We talked about detector tapering, passive shielding, active shielding, use of physically segmented composite detectors and all that. The active shielding was a typical example of this electronic logic being used to select out the full energy peak events and remove the background events. So one particular example we have already studied is active shielding. Right. So now we are going to study other cases. So first of all, the question is why? Why two or more detectors? Why not just a single detector? Okay. So let me now rub this part entirely. Okay. Now suppose for the time being, let me think that I am just using a single detector. You are late. Okay. Suppose for the time being, let us think that we have used only one detector to study this nucleus B star. So this is the detector we have placed. Okay, and we are studying whatever is coming off from the detector. Now what do you think you will expect? You expect to see in the spectrum. Suppose this is the spectrum, this is the energy. Okay, and these are the counts. Now here in this spectrum, you will see the effect of all of these nuclei and these particles as well. Right? I haven't told you about the type of the detector. I have just told you that I have placed just one detector to study all these possibilities. Just how many detectors? Only one detector I have placed. So effectively you assume that I am going to study 1, 2, 3, 4, 5, 6, 7, 9, 10. So these 10 products will be there. Now consider each of the nucleus X1. During decay, suppose each of them, they emit, say for example, 30 gamma rays. Each of them, they emit 30 gamma rays. So how many gamma rays will be there total? There are 5 nuclei, 30 into 5, 115 gamma rays, right? And there are so many particles as well, plus particles, right? Which particles? Proton, 2 proton, then alpha neutron, of course neutron will be there, right? All of them. So can you think what this spectrum will be? This will be very cumbersome, very difficult to decipher, something very complicated. So complicated that we will not be able to extract a single information from all of them. Okay, we won't be getting anything. So single detector is of no use in this particular case. This you have to understand. So this is an important question. What is the difficulty we face while selecting a particular channel using only one single detector? This might come in your examination. So the thing that I am explaining right now is your possible answer. Okay. So complicated spectrum, extremely complicated spectrum from which we will not be able to get any information. Right? So what do we do? What do we do? Tell me.
Amplification.
Increasing
the number of detectors.
Yes. Now, remember in classical mechanics, in college days, we have learned something. In order to solve some problem, we have to identify how many degrees of freedom it has. Then we have to act accordingly. Okay. Now see here, there are so many parameters, so many unknowns, each of the nucleus. Now, isn't it better to use more than one detector? Say for example, in this particular case, let me use a charge particle detector, CP detector, then a neutron detector. Charge particle detector I am using again of say two types, one for proton, one for alpha, and neutron detector is again only one type for just a neutron detection. So how many detectors I am going to use? 1, 2, 3. Next, so with this basic idea, with these three types of detectors, basically I am considering to understand the spectrum due to all these charged particles. You understand? This is what I am trying to solve. So I have divided the entire problem into two parts. First is your charged particle selection in this case. Okay. And next, to understand this, the gamma rays getting emitted from this nuclei, we will be using gamma detectors. Okay. And then we have gamma ray detectors for Xi nuclei. Xi, I running from 1 to 5. Okay, so all those nuclei, for that we have the gamma ray detectors. Look closely. This is our plan. This is how we are going to proceed. Now, till now we haven't introduced any trigger, anything. We haven't done anything. We are just trying to understand the problem and writing the algorithm effectively. What steps we shall do. And now comes the trigger. Suppose you want to study X3. What should be the condition? Tell me. Suppose I want to study this X3. Now, along with X3, alpha is being emitted, right? So, I should put the condition will be detect alpha. Okay? Any more condition?
One.
Very good. Detect single alpha. Next, any more condition? Let us put AND operator. And do not detect proton. Right? Again, and do not detect 2 proton. Now when I say do not detect proton, this I am going to rule out. Again 2 proton I am going to rule out. Of course, if I just detect single alpha, they will not be coming. But there is a possibility, try to understand, that out of all these 5, which are dominant reaction possibilities due to the decay of the compound nucleus B star, there can be some other channels like your, say for example, alpha 2pn plus say X7, this type of reaction where the production cross section is very small, but there is a possibility. So if I just put the condition that detect single alpha, this will enter into my considerations. So I have to get rid of it. Try to understand. There may be products out of these 5 possibilities. So I have to rule all of them out. That's what I am doing over here. Similarly, there will be AND. Again, no neutron. Then AND what? That's it. No alpha n. Something like that. Similarly, no alpha, no NP, and so on. So you are able to understand probably what I am trying to get over here. So this logic that I am putting, this is basically an example of trigger. Now I have to implement this using digital logic. Okay. Just as we have done in our anti-coincidence case. Okay. But first, writing this down out of considering the physics case is important. Next, let me tell you about the selection of proton, alpha and neutron detectors. You see, any detector, I have already told you, it will never be efficient. Suppose I am taking one proton detector. Now that detector will not be efficient for all proton energies. Okay. So I have to know before doing the experiment what proton energies I am expecting. So you do calculations first, compound nuclear calculations. Say for example using the PACE program, PACE 4 and other programs, you can get an idea of the range of energies the proton will be getting out. Okay. So for that particular range, you choose the detector accordingly. So you choose the detector for which is efficient only for this particular range of protons being emitted. Okay. So this is very important. Careful selection has to be done. Same for other alpha and neutrons. So this is what I am doing right now. Not only I am telling you about the trigger in nuclear physics, but also experimental planning. How we basically plan a compound nuclear reaction experiment. This is one of the most complicated reaction experiments. Okay. Comparatively, direct reaction is not that much complicated to analyze. Now, in certain cases, if we have a medium mass nuclei, then a single nucleus can emit more than 100 gamma rays. So think of it, life will be so difficult. Okay. Any questions?
Sir, before the experiment, how can I select a particular logic for which can be worked on for my experiment?
You have to understand before doing the experiment, when you do the PACE calculations, you will know that if I react this at this particular lab energy, then these are the possibilities. Before doing the experiment, you do the PACE calculation and you know beforehand that these are what I am going to expect. These are the energies. The calculations will also tell you about the cross section for each channel as well. You don't have to do it by your hand. You take the help of this PACE 4. Try to download this app. I don't think it's available in smartphone. You have to use a computer. Try to download it in a computer and try to see what happens. Okay. Say for example, take any nucleus. There will be test cases over there. Maybe we will talk about PACE 4 calculations in some other class. But this is what actually happens. We just don't do an experiment randomly. Because you see, right now, when we are in this class, what is the cost of electricity? All the fans and light, it's not very much. Maybe during this entire period of class, maybe less than 10 rupees. But to do an experiment for 1 hour, sometimes the cost is more than 50 lakhs or 1 crore. Because mainly of the beam, type of beam, whether you are using stable beam or radioactive beam. So you understand, 1 hour is so much costly. So we can't do anything just on the base of any false ideas or anything. You have to be very much sure. Before doing an experiment, you have to plan very carefully. Do lots of check if there is something wrong with your planning. Okay. So there are tools to help you in doing the experimental planning. Now suppose I am able to successfully select out this channel. So alpha plus x3, and now I am using, say, two gamma detectors, say detector 1 and detector 2, gamma detector 1, gamma detector 2, to study this nucleus x3. Okay, so how do I do the study? Basically, in each of the detectors we take least mode data. What is that? First is the timestamp. Timestamp. Okay, one particular time, and then what signal we are getting in the two detectors. Amount of deposited energy. That's it, nothing more. Now, later on, when you do the software analysis, you can generate the spectrum. So the spectrum will be like this. This is energy, gamma energy, and this is spectrum. Say for detector 1, this is counts. Again, the same thing you will get for detector 2 as well. Okay, counts, energy, and for detector 2, the same thing. But this doesn't help us, right? Because still, when I am choosing just detector 1, effectively I will be seeing this time I will be seeing, say for example, this x3, say for example, every 30 gamma rays. So effectively I will be seeing around 30 gamma rays, you expect, in each of them. Here also 30, here also 30. Okay, so the problem still remains. Previously we have a very complicated spectrum, now we have a little less complicated spectrum. But still the spectrum is complicated. Okay. Why? One of the reasons is, you must remember the 662 spectrum of 137 cesium. When we do experiment, remember what happens is this. This is the typical structure. This is the full energy peak. Okay, good. What is this? This is the background. Remember? This is the background. Now, let me rub this part. The actual problem in experiments, I am going to talk about. What's the major problem? The problem is that when this was just monoenergetic gamma ray. Okay, monoenergetic gamma ray, only one gamma ray, 662. Fine. Suppose I have got two gamma rays, one over here, one peak over here, another peak over here. What do you think you will get? Because of this peak, you will get something like this. This is the Compton background of this peak. Okay, and for this other peak, you will also get a similar Compton background. Okay, but they will to add up in their common region. So effectively, what you will be getting is something like this. You try to understand, this is what you are getting. Because of the adding up of Compton backgrounds. So the more number of peaks we have, this Compton background addition will cause a huge issue in peak identification. Now you are understanding why I am telling you that our very complex problem has still become little lesser, but still it's a complex problem because of all these Compton backgrounds. So what do we do now? What's the way out? You see, what we can do is the following, which is known as generation of a coincidence matrix. Basically, what we can do is we put the spectrum data of detector 1 over here and detector 2 over here and try to see the result. What will you get as a result of this? This is basically, if you see a single point in this spectrum, then what will it mean? Tell me. Now look closely what I have done. This is sort of a level scheme of this X3 nucleus, okay, that we are studying. Very basic structure. In real life experiment this doesn't happen, but for understanding this is good enough. So how many levels? This is the ground state, okay, first excited, second excited, third excited. So I have considered only 3 excited states for X3 nucleus. Fine. Now from the third excited state, second excited state, first excited state, gamma emits, and gamma is gamma 1, energy E1. Look closely. Goes to second excited state. Again, from here gamma 2 E2, and from here gamma 4 E4. Next, third to first is gamma 3 E3. Okay. Now the energies I have just plotted in this detector 1 and 2, this energy axis. This is just the energy axis for each of the detectors. Okay. So now in the case of detector 1, if I choose E1, which means that if I detect this gamma, choose E1 means I am detecting this gamma in detector 1, then there is a possibility that you will get the coincident gamma rays in detector 2. What are the coincident gamma rays? Is this a coincident gamma ray? No. Here the coincident gamma rays are E2 and E4. So if I try to put a coincidence condition on E1, I might find some counts in E2 over here and in E4 over here. So basically now we are talking about coincidence matrix. See, next, suppose I am putting a condition, I am detecting E2 in detector 1. Which one will be coincidence? E1 and E4. See, if I detect this one, then these are the coincidence with it. So here E1, this is this one. See, this one, okay, and E4, again this one. Next, if I detect E3 in detector 1, which one will be coincident? Only E4. So E3 corresponds to only E4. Next, E4. If I detect gamma 4, then which one will be coincident? All 3. See, because this is also coincidence with this. So basically I will be getting something like this. 1, 2, so 1, 2 and 3. Okay. Now try to see this from the detector 2 axis. So suppose I detect again E gamma 2 in detector 2. Which one will be coincidence? E1, gamma 1 and gamma 4. See, gamma 1 and gamma 4. So this matrix is symmetric. See the structure. See the structure. So we are talking about a symmetric matrix. Okay, try to write down whatever I am saying. All these things will come in the examination. I am telling you, it will be coming. Okay. So now you see, I am just talking about two detectors. It's possible to create a cube where we will have three axes. Okay, detector 1, detector 2, detector 3, and then a hypercube where there will be 4 axes and hypercube 5 axes, and that is possible if we have got so many detectors, right? Normally in nuclear physics experiments nowadays we have large number of detectors, more than 20. So this is the basic idea. So if I detect one gamma ray, then I am getting an idea of which one is coincidence with it. Similarly, here also, if I detect this one, I will get an idea of which one is coincidence. So this helps me, this correlation. So basically, I am taking two detectors right now over here and trying to get a correlation between them. And this will help me identify the coincident gamma rays in the spectrum. So that's the basic idea.